All right, we did a lot of work on this already. One of the things that seemed to be holding people up from seeing these quadratics was having that e to the x stuff in there. So the easiest way to get rid of that, get rid of all the junk that makes it look like alien language, is to just substitute and pull that out. And when we do that, you know, sometimes things work out nice, sometimes they don't. I mean, this was an example of when it doesn't. So with this one, we go back and we say, all right, we got this w business, but because we substituted in, that means really e to the x equals 5 plus the square root of 26, and e to the x equals 5 minus the square root of 26. One of those is undefined. One of those is not going to work. Which one is it? The negative. Which one of these comes out to be negative? Definitely down here. The square root of 26 is going to be bigger than 5. So when we subtract, that one is going to come out negative. So this is undefined. But we still have some math to do with that little e to the x up there, and that would be to take the natural log of both sides. And get that to 4 decimal places. Whatever that comes out to be. I'm punching it up here so you can see it. I'm just going to cheat and give it to you, but better punch it in. So, natural log of 5 plus the square root of 26. Oopsie. Thank you. Insert a 1. Oh, wait a minute. Oh, why was that there? Natural log, how did I hit a 2 for 5? Well, 5 big fingers, I guess. You know, that's better. 2.3124. Is our approximate answer. And again, these can be checked. You know, we could go back and put it in. It's going to be approximate, though, because we round it, unless we work backwards and leave our answer as it is and go all the way back up to the beginning and put it in. But it is checkable. It's just that we have to be careful. So down here in day 2, we're starting where we're going to solve logarithmic equations. Now, in Algebra 2, you didn't have very tough ones, because what we did was we condensed everything and we snail shelled them. Magic. You know, we had nice answers. We know that magic isn't necessarily going to happen with everything we're doing in pre-calculus or anything that we're doing in math. So solving logarithmic equations, when solving logarithmic equations algebraically, it's important to keep track of the domain. So what we have to do is figure out, is the domain changing with any of the math that we're doing? Because if that happens, we're probably going to have extraneous solutions, and we don't want to do that. So keep track of that domain of each expression in the equation as it's being solved. A particular algebraic method may introduce extraneous solutions, or worse yet, lose some valid solutions. And we actually had an example of this yesterday. I'm just going to give you a real basic example right here. And that would be if, to solve this, we decided we're going to divide both sides by x. We're going to lose a solution. This is an x squared. There should be 2 solutions, but if we do this, we've lost one. And we recognize, hey, degree is supposed to tell us how many answers this has. So I should not go about this problem that way. If I want to get my 2 solutions, I'm going to have to move everything over to one side and do some factoring. And then I'll get my 2 solutions. So the domain is important, along with how many solutions should we get. And we want to know in advance when we're working through those things. Because algebraic manipulation of a logarithmic equation can produce expressions with different domains, it's good practice to check your solution graphically whenever possible. We won't necessarily do that every time, but you know, we know we can do it, and on the few that we have the little boxes for the graphing calculator check, maybe we'll stop and do that. So, when solving logarithmic equations, method A, the good old one from Algebra 2, condense to a single logarithm, isolate the logarithm piece, convert to exponential form, or exponentiate both sides. That's the snail shell there, and solve and check. That's what we've done in the past. Method B, get 1 log on each side, and then use one-to-one properties, which means I don't want to use a special one. They both say logarithm base 2. That part is already equal. The only way this is going to come out to be equal expressions is if x equals 6. That's a one-to-one property. We already know that the basis for the logs are the same. In order for the entire statement to be true, x would have to equal 6. And then, like it says, solve and check. Now, it makes it sound a lot faster and easier than a lot of these will go, but it's a good place to start. So down here, it says, solve the logarithmic equation algebraically. Now, one of the things we want to do is think domain as we go through a problem. So as I look at this, I realize that the x portion of this is actually linear. It's an x to the first. So we should only get one answer. As we do the solving, we may encounter two answers. We'll know one of those has to be extraneous as we do that. So the first thing we're saying is just do what you know from Algebra 2. Make the snail shell. 3 to the 4th equals x plus 2. We know this is 81. We subtract the 2. And we get 79. And it works. The other way, which you don't teach a lot in Algebra 2 just because it's kind of goofy. When you're first learning how to do these, it would just seem really weird. But truly, logarithms are inverses of power statements, where we know the bases match and we have an unknown power. So we could do that. I know that looks really weird. But it's taking 3 and raising it to each side of this. These would drop out and we would get x plus 2 equals 3 to the 4th. It really is what we're doing when we make the snail shell. It is. But it just looks really weird to us. But sometimes it works out nicer. In this case, it's going to give us the same answer. It doesn't make any difference. We're still going to have an 81 over here, and we're still going to subtract 2 from both sides and get 79. But it's just knowing, hey, there are different methods out there, because sometimes the usefulness of one method versus another helps you a lot when you get to calculus. Now, for both of these, got one answer. We're supposed to get one answer because it was linear to start with, so that worked out well. This little bugger down here does have a base, even though it's not there. What is its base? 10. So we can snail shell this one. Say that's 100. Thinking of domain here, this is supposed to have 2 answers, so this is actually supposed to be like a quadratic with 2 solutions. Well, I'm going to take the square root, and that'll give me the plus or minus. Which makes me a little nervous. This is logarithms. And with logarithms, we can't evaluate negative numbers. But if you put this back into the formula, is that a problem? Order of operations says we're going to square it first. So those are our 2 solutions, plus and minus 10. Now let's just say instead we did this. Hey, one of the properties of logarithms is that you can bring that power down in front and make it multiplication. Do that instead. Well, now I'm going to divide by 2. Bless you. Well, now I can snail shell, and it's easier. 10 to the first equals x. What happened? I lost a solution. So, using the properties of logarithms, not always necessarily the best idea, you know. We would have to realize, wait a minute, this was quadratic up here. It should have 2 solutions. What on earth happened, you know? And when we graph it, we would definitely see that. So that's the other piece we need to do. Where we grab the calculator and we say, all right, we need the log of x squared. And we want to know when that hits 2. So I'm just going to try Zoom 6. Oh, it has has two spots where that is happening, you know? And so at that point, you would realize, wait a minute, I missed something here by solving it this way. I better go back and solve it a different way. And when you do that, you'll find that other answer. So maybe we better put a little sketch of this on here. Like so. So the answer is the same, new, because in the second one we lost an answer. We lost a solution. Using the properties of logarithms. True answer. Plus or minus 10. Because we keep our eye on the domain and the fact that we know how many solutions we're supposed to have as we go through it. And if we do that, then we would know we're wrong, and we could maybe grab the graphic calculator and try to figure out, okay, how did this go wrong? What happened here? So now they're getting a little larger. Solve the logarithmic equation algebraically. Okay. So, well, I know I'm supposed to get the logarithm thing all by itself, so I can snail shell. So I'm going to subtract 4. I'm also keeping an eye on how many solutions I'm supposed to have. How many should this have? Just 1. Is that x that we see up there for that domain? That's next to the first. Then I divide by 30. Now what? Snail shell. Worked out pretty slick. And we get, oh, well, as an exact answer, we could leave it like that. But, let's see. They want their decimals, of course, we've got 40.5 as a backup. Checkable? Yeah. You have to use the change of base formula as you went through it. But you definitely could. In fact, you could check this one by hand, because this is going to be a really nice little 81 in here. And you could snail shell it in your head and check it as you go. Or you could graph it and check and make sure that that's going to be your one solution there. D. I wonder how many solutions that's going to have. How many? We will have 2. Because if we truly did, addition is going to be multiplication. If we truly did multiplication here, this would give us 2 solutions. So something to think about in the back of your mind as you're working through this problem. Okay. Normally, in algebra 2, if we did this, we would condense and we would snail shell. So let's condense and let's snail shell. Yuck. Oh yeah, they're not all pretty. So do a little FOIL action in there. X squared minus 1x plus 2x minus 1. Oh, no base. What is there? 10. Yeah, common log. Base 10. Oh, I like that. 10 to the first equals x squared plus x minus 2. That's just 10. No wonder. Easiest way to solve quadratics is to factor them. And use this factorable. Let's see. We subtract 10 on both sides. Factorable. What are the factors? So our 2 solutions are Negative 4 and 3. But wait a minute, this is logarithms. The negative one might not work. Go back up, put the negative 4 in that. Is that going to make either one of our parentheses up here negative? So that we're saying we can raise 10 to a power and get a negative. Is that going to mess that up? It is going to mess it up. The negative 4 is extraneous. So we don't have negative 4. And now we say, wait a minute, it was a quadratic. It was supposed to have 2. Well, remember, it might have 2, it might have 1, and it might have none. So it's not necessarily solid 2. That's, perfect quadratic situation. Remember, quadratics can bounce off the x-axis, and then they really only get 1 0. And there are times when a quadratic never crosses the x-axis. So this is another one where you maybe want to plug it into the graphing calculator and make sure it's only going to hit at that one spot. So the method from Algebra 2 is still working, so that's good. Oh my goodness. Yeah. Look at that. Can't even venture a guess as to how many answers this has right now. There's so much junk going on here. So what I do instead is I look for, hey, what do they have that's the same? Because that might be a clue. Oh, that's the same. So maybe if I condense this, some of this stuff's going to cancel out. If they have so much that's alike. So let's see. Well, this 2 came from where? It was a power. That 3 was also a power. Got that done? What does subtraction do in logarithm language? Divide. Oh, yeah. Now we see it. 2 of those are going to cancel out. We've got an x minus 5 squared on the top and x minus 5 to the third on the bottom. But 2 are gone. Now, if at this point somebody said, you know what, I'm going to make that x minus 5 with a negative 1. You can do that, or you can keep going with the snail shell. What do you guys want to do? Snail shell it. 4 to the first equals 1 over x minus 5. I'd slap a little 1 underneath that 4 and cross multiply here. So that will give us 4 times x minus 5 equals 1. If we want to solve it, we're going to distribute. And then we'll keep going. We'll add 20. And we'll divide by 4. And if we wanted a decimal, well, we didn't even do it. The decimal doesn't work out so nice. Too tough though. It's going to go in 4. Yep. 5.25. Were we supposed to have 3? I mean, there was something up here that was a power of 3. Were we supposed to have 3 solutions with this one? You want to look at it in simplified form before you determine how many we're going to need. So once we had this simplified, this was an x to the first. So we should just have one answer. It's positive. Chances are pretty good it's going to work. But again, you could, I don't know that I would, look at this monster up here, but you could put this in as y sub 1 and put that in as y sub 2 and, let the calculator do. You'd have to use the change base formula again, so it'd be kind of ugly. But the 5.25 would work. All right. Method B. Ooh, that B sounds kind of scary. All righty. This says 3x minus 2 plus x minus 1 equals 2 natural log of x over there. So with method B, here's what we're going to do. We're going to try the same thing where we say, hey, we would condense this. But things are going to get a little weird because there's a natural log on both sides. Okay. But if it said natural log over here and natural log over there, then we could just drop the natural logs out because it would have that one-to-one relationship. So I'm going to put that 2 back up there. And I'll go ahead and do the FOIL on this. So natural log of 3x squared minus 5x plus 2 equals natural log of x squared.
Did you get the square?
This one?
Oh.
This 2 is out in front. Put back up as a column. Now, does everybody see that the natural logs don't matter anymore? The only way this is going to be true is if 3x squared minus 5x plus 2 equals x squared. That's the only way this is going to work. They both had the natural log of it. That's not the issue. The issue is, what are we doing with the x's that's going to make this true? Because the natural logs are already there. All right. Hope is always to factor, so we need to move that x squared over. Now, maybe you wouldn't want to waste a ton of time if it's not factorable. So remember, you can always do b squared minus 4ac. If the discriminant comes out to be a perfect square, then you know it's factorable. But I'm going to flat out tell you this one's factorable. So let's see if we can find it. With 2x squared, we know it's going to have to be a 2x and an x. And in the back, we have a plus 2, and in the middle, we need a negative 5. So they both have to be negative. It's just about placement, which one needs to go where. So with the 2x, do I put a minus 2 here, or do I put a minus 1? And that means it has to, right? It has to. So now, we're going to get 2 solutions here, and I think back. That would make sense. Plus means multiply. Got a quadratic. Should have 2 solutions. This one is the obvious 2. This one, you add 1, you divide by 2, and you get 1/2. Huh. Let's check this out. Let's punch this in. Let's see. So I've got natural log of 3x minus 2. Notice the ones they're having us do the punching in for are either common log or natural logarithm. The other ones using the change of base formula is just a pain. So natural log of 3x plus 2 plus natural log of x minus 1. We want to know, what does that equal? 2 natural log of x. And we might have to mess with the window here, but let's try to do 6. So the question is, are they really hitting at x equals 1/2 and at 2? Let's see, second trace, number 5, Blinkster, it's right there. I want to know, when are they hitting each other? And Blinky wanted me to move him away from 0, 0. So it says 2 is good. Whoa, what happened to the 1/2? Are they hitting each other at 1/2? We can see that at 1/2. How do we get that? Well, remember, quadratics might have 2. They might have 1. They might have no solutions. So we got an extraneous. If we put 1/2 back into this, it is not going to work. It isn't. So, you know, especially if it's log, common logarithm, or ln, take the time to plop it into the calculator just to make sure. So, good solving. Now we got a couple of massive ones here to look at. Solve the logarithmic equation algebraically. Woohoo! All right, well that leaves it wide open for us. Well, normally we would condense, see what we have, go from there. So this is addition. What's addition in logarithm language? Now, that might produce an extraneous solution. How do I know that? We just made this an x to the third, you know? And it's possible whenever we raise things to power like that, something might happen. So we're keeping in mind it might have 3 solutions, it might. But we kind of keep in mind that, you know, we just raised that power up there. What do you think we ought to do now? Don't need them? Don't need them. Logarithm base 2 is on both sides. Could be 3 solutions here. Should we divide by 3? Take the cube root. Let's divide by 3. Let's see what we have. If I cube root right now, bless you, am I going to see 3 solutions? So I back up a step and say, okay, factoring. That's how we like to solve everything in algebra. So I'm going to go ahead and set this equal to 0 and go, oh, that's a difference of 2 cubes. Oh, I remember that formula, right? This one is always just really logical to me. If it's a cubed minus b cubed, pretty obviously there has to be a factor of a minus b in there somewhere. And then everything has to work forwards and backwards in math. So a times something has to give me a cubed. It has to be a squared. B times something has to give me b cubed. It has to be b squared. And notice there's no middle term. And if there's no middle term, then what we have for a middle term has to be undone by this sign. So if this is a minus, this has to be a plus. That's the only way that's going to happen. So again, I just kind of logically think through how that formula would be set up. So now, we're saying that a would be x, because x cubed is x cubed. And that b would be a little 2, because 2 cubed is 8. And we're going to plop it in this formula and see what happens. So that would give us x minus 2 times x squared plus 2x plus 4 equals 0. Hey, we got one nice one. That's a nice one we would have gotten had we taken it anyway. Right there. But there might be some more over there. So the first thing I'd check is, hey, is that a perfect square trinomial? This is x squared, this is 2 squared, x times 2, double it. Ooh, no. Is it factorable? 2 numbers and multiply to 4 and add to 2. Not happening. This won't take us too long to complete the square. Got a nice little b value. A is 1. Okay. 2 divided by 2 is 1. 1 squared is 1. Oh. There is a negative on the right-hand side. And when we take the square root of that, they're going to be imaginary. But we needed to do this process so that we can see these are not going to be real solutions. Bless you. Goodness, lots of sneezing today. So these two, not going to work. That one was a go. But we couldn't be sure until we could see in factored form, hey, the possibility for all 3 zeros is here. You know? But we ended up with 2. And remember, cubics might have 3 solutions. They might have 1 solution. That's it. That's what cubics do. They've got to cross somewhere. 3 or 1. Alrighty. Another whopper right here. But we have a new problem. We can't condense those. How come? They don't have the same base. Man. So, big hint. On the ugly one, use the chicken base formula. See what happens. So this would be the logarithm of x squared over the logarithm of 100. Oh, why is that? What about that is a positive? What is a logarithm base 10 of 100?
How are you able to just divide it?
That's the change of base formula. It's what it does for us. The change of base formula says if you want to know what this really is, take the logarithm of what you're trying to evaluate and divide it by the logarithm of the base. And it's going to work every single time. Now, that's interesting because I'm thinking, you know, dividing by 2, that's the same thing as multiplying by 1/2. And since this is a logarithm, where's that 1/2 really coming from? The power. When it's power to a power, don't we just multiply? Oh, we had to do that first. I mean, if we're going to have like bases as we go through here, we had to realize, hey, that little monster, that is simplifiable. So let's go back up and substitute that in for this train wreck right here. Now we know it's just log of x. Oh, actually, I'll use a different color now that we've got that simplified. How many possible solutions are we talking about here? 3, but is it simplified? So maybe we better hold off. We're thinking right now 3 so far, but maybe there's something else we could do. Subtraction is? Division. Oh yeah, look at that. One of those x's is going to cancel. Now what you think? Snail shell it? You got a base for me? And I'm going to leave that 10 to the 6 there for a little bit. I'm not going to mess with it and put a whole bunch of zeros on that. Take a proportion and cross multiply. Well, I'd have to divide. Okay. So how do I get the x by itself? Normally I'd say square root, but you know what's going to work really nice over there this time is if we just raise it to the 1/2 power. We're working with scientific notation here. So if we raise both sides to the 1/2 power, it is like the square root. We're still going to get our little plus or minus. And the square root of 1 is still 1. But the nice thing about leaving it 1/2 is that a power to a power means multiply. And 10 to the 3rd, that's 1,000. So without having to write all those extra zeros all the time. But now I have another worry. We just got a negative answer. Go back up there. Are we going to have a problem with a negative answer, -1/1000 for either of those? Not the first one, right? But the second one's an issue, isn't it? The negative's out. After we simplified this, we had an x squared. That means it could have 2 solutions, but with quadratics, you can have 2, you can have 1, you can have none. We got 1 solution that works, so we've got it. You know, 1 extraneous and 1 solution that works. So now, I better check this out. So we get a little start on all the blah, blah, blah. The word problems from this section, they make people cringe a little bit, but they're actually really easy once you learn how to work with them. And that's because we talk about this thing called orders of magnitude. In Algebra 2, you talked a little bit about the Richter scale, not a ton, a little bit with the Richter scale, but orders of magnitude help with that. Order of magnitude of a number is the integer portion of the number's common logarithm. Integer portion of the number's common logarithm. That means not the decimal stuff that's behind it. So two numbers have the same order of magnitude if the integer portion of their common logarithms are the same. Same order of magnitude if the integer portion of their common logarithms are the same. Order of magnitude is used to make approximate comparisons of like quantities. Comparisons of like quantities. Kilometer. 3 orders of magnitude longer than a meter. Okay, a kilometer is 1,000 meters. So they're saying from 1 meter to 1,000 meters is 3 orders of magnitude. That's got me thinking that it just has to do with tens, but that's only one example, so I'm going to check out another one. $1 is 2 orders of magnitude greater than a penny. Well, $1 would be 100 pennies. Well, now that can't just be a coincidence. So, orders of magnitude, this one was 10 to the third, this one was 10 squared. Let's try one more. A horse weighing 400 kilograms is 4 orders of magnitude heavier than a mouse weighing 40 grams. Kilograms, there's 1,000 of those in a gram. So we've got to add 3 zeros to that. So let's see if the theory is right. Did they add 4 zeros to 40? They did. So it has to do with powers of 10. 8 million people, 6 orders of magnitude bigger than Earmuff Junction with a population of 8. So it has to do with powers of 10. So that's what that orders of magnitude part is. And that explains why they kept talking about the common logarithm. Common logarithm has a base of 10. So if we see that common logarithm, we know orders of magnitude are more. So using a calculator, compute the logarithm of 4 times 10. Okay. Logarithm of 40. Uh, 1.6021. Okay, so next one will be a logarithm of 400. 400. 2.602. Oh, that round to 1. Wait a minute. Look at all those decimals. They're the same. How about 4,000? Log 4,000. All the decimals are the same. That looks really bad right there. That was supposed to be a comma. So going up by a power of 10 increases the integer portion of that logarithm. So 2 says, what's the pattern in the integer parts of these numbers? They are increasing by 1 for every power of 10. Increasing by 1 for each power of 10. And it's squishing that in there. What did we see about the decimal parts? They're all the same. Are the same. How many orders of magnitude greater is 4 times 10 to the 10th than 4 times 10? Yeah. That's 10 to the first. Remember, it's about powers of 10. 9 orders of magnitude. What we have there. So orders of magnitude are used to compare. Like it says, all of these are logarithmic scales because we're talking about either really big numbers or really, really teeny numbers. Sound or noise, the bell measures the order of magnitude in decibels of its intensity compared to the threshold of hearing. Severity of earthquakes, Richter scale, really big numbers. Acidity of chemical solutions, pH. So now, you know nothing about earthquakes. You know, they said at some point when I was growing up, I remember on the news they said we actually had an earthquake in Minnesota. It's very rare that we do, but you couldn't even feel it because the air, we just don't get big fault lines and earthquakes and that stuff in Minnesota. So when somebody tells me the Richter scale for earthquakes, I don't know, is it a big one? Was it a small one? What is it? So we want to know how many times more severe was the 2001 earthquake in India with the Richter scale of 7.9 than the 1999 earthquake in Athens, Greece, where the Richter scale was 5.9. We have this lovely little formula right here that gives us the Richter scale calculations that they do. So what I see is this. I see that the India one would have had the logarithm of A, which is some amplitude, and I don't know what it is, I'm just going to leave it A sub 1, over the period of the seismic wave, and I don't know that either, I'm going to make that T, the period of the seismic wave, plus some B, which was the weakening of the seismic wave with increasing distance from the epicenter. Okay, they have different amplitudes. However, the period that they use, because it's the Richter scale, tends to be the same, and the speed value to be the same. So that one came out to 7.9. That I know, they gave me that. Well, the second one had a different amplitude, and that came out to 5.9. So what would happen if I wanted to look at the difference between the two, because that's what we're supposed to do. We're supposed to say, well, what happens to the difference between these two that makes this a bigger earthquake? So I would need logarithm A sub 1 over T plus B minus logarithm A sub 2 over T plus B and 7.9 minus 5.9, come off to 2. Now wait a minute. If we take this and we subtract this, aren't the b's going to cancel out? Isn't b minus b going to be gone? Okay, so then this will say logarithm A sub 1 over T minus logarithm A sub 2 over T equals our 2. We would want to condense this to solve it. What's subtraction mean? Division. So this would be the log of A sub 1 over T divided by A sub 2 over T equals 2. Wait a minute, I think the T's are going to cancel out. A sub 1 over T times the reciprocal T over A sub 2. T's are gone. Logarithm of A sub 1 over A sub 2 equals 2. There's a climactic moment that we're missing because of that clock. We'll start there tomorrow. Doggone it.